Jared?
64.
3. Jared, can you explain how you got 64?
Just knew it.
Just knew it?
I knew it.
Okay, Elizabeth?
I knew that 20 and 30 was 50, and that 9 and 5 was 14. And so I took 10.
Double column addition is usually taught by giving rules to children to follow. In this way of teaching, children are told to add the ones in the right-hand column first, and then add the tens. The research and theory of Jean Piaget show that children acquire logical mathematical knowledge not by internalizing such rules from the environment, but by construction from the inside through their own natural ability to think. An approach to first-grade arithmetic involving the addition of small numbers such as 5 and 9 was published in a book called Young Children Reinvent Arithmetic. As the title suggests, children can reinvent addition on their own without any instruction in the traditional sense. If children play dice games and add 3 and 3, 4 and 2, and so on, day after day, they will remember the results of these actions without any lessons, worksheets, or reinforcements by the teacher. What about double column addition? Rob Medell found in a private school in New York City that if children are encouraged to think in their natural ways, they universally begin by adding the tens first, before adding the ones. This is what we also found, as you see in this discussion. It took place in a second-grade classroom in the middle of a school year, early in February.
Celsi?
101. Disagree. Disagree.
Brian, what did you get?
10. Disagree.
JC?
111. Agree.
Okay. Who wants to try to explain how to get the answer? All right, JC?
I know that 80 and 20 is 100. And then I knew that 6 and 4 was 10. So I took the 7 and 4, and that made 11.
Okay.
Agree. That's how I did it.
You disagree with yourself? Which do you think it is now, Brian?
111.
Okay, Celsi, what about you? Do you still think it's...
111.
Okay. Let's go on to another.
Let's look at how our children invent subtraction in problems such as this one.
See? Eighteen. 11. Carrie Lynn, come here. What'd you get? Okay. Okay, got that one?
9.
Okay. Have that one? Okay. All right. Anyone else? Okay, I'm hearing a lot of 18 and a lot of 11, and a lot of people are saying the answer is 9. So we have 3 more answers again. Does someone have something we don't have up here? All right, how many think it should be 18?
I can prove it. I can prove it's 9.
How many think?
I can prove it's 9.
All right, how many think it should be 11? 2? How many think it should be 9?
I can prove it's 9.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
I can prove it. I can prove it's 9.
Okay. Gary, we'll let you try first. What do you think the answer is?
See, you take the last answer. 9.
Okay.
See, you take, like I did last time, you take the 6 and the 7 off of the 17.
Okay.
And then take off 10, and that will be 10, and take off 7 more, and that will be 3, and add the 6 back on, and that will be 9.
Okay, so 20 take away 10 was 10. You do.
I can make it.
What was your answer?
It was 18.
18. All right, Elizabeth.
I took 10 off the 20, and that was 10. And I took 6 off the 7, and that was 0. And I took 1 off the 10, and that was 9.
I can prove it's 11. 20 and 10 is 10, and 6 take away 7 is 1, and 10 and 1 is 11.
Disagree.
So Stephen has a different answer. Stephen says 20 take away 10 is 10. And he says 6 take away 7 is 1. And 10 and 1 is 11.
Disagree.
The explanation of the next child, Grace, is impossible to follow. But when children try to give an argument that will convince somebody else, this thinking in itself helps them learn arithmetic.
You can't take 20. If you took 20 away from, you had 20 and you took away 10, how could it be 11 because you're taking 10 away? I can tell him. See, Stephen, you'd have to have 21 to take that 21 away with the 10, and you'd be taking away 11. Grace, you don't disagree. I'll prove it's 9. I'll prove it's 9. Stand up.
All right, Chris.
All right, you see?
Stand up.
Me too. You see, 10 take off from 20 is 10. All right? And then add a 6 on it, 16. Minus 7, it's 9. I can prove it's 9 too. I think everybody that thinks it's 9 stand up.
Now, Stephen, what do you do?
I know.
I disagree with myself.
You disagree with yourself?
I know.
Are you sure? You sure you're not right? You sure it's not 11?
I'll explain.
Okay, Tracy.
All the children subtracted 10 from 20 first. However, they dealt with the ones in 3 different ways. Elizabeth said that she could subtract only 6 from 6, and therefore had to subtract 1 from 10. Gary subtracted 7 from 10, and then added 6, but Chris added 6 to 10, and then subtracted 7. Stephen's answer of 11 is familiar to all teachers who have taught subtraction of this kind. Piaget said that if children make errors, they make them because they are intelligent and think. The teacher's job, therefore, is not to correct the children from the outside, but to create a situation in which children might correct themselves. Piaget's theory about the nature of logical mathematical knowledge convinces us that children are bound to arrive at truth if they argue long enough. This is why we bring out wrong answers and encourage children to exchange points of view. Whether they are right or wrong, children construct knowledge more solidly when they are encouraged to defend their ideas. If they become convinced that another idea is better, they will change their minds. This is why the teacher refrains from saying that an answer is correct or incorrect, and instead encourages children to agree or disagree with each other. You're perhaps wondering how this teacher got started at the beginning of the school year. Let's look at the same children on October 1st, 4 months earlier than the session you've just seen.
Right, let's start off with a problem such as 9 plus 6. Okay? Raise your hand if you have a way to get this answer by thinking about it. Good, lots of hands are up. All right, Chris, I think I saw your hand first.
All right. This is how I think about it. I think as if 9 were a 10 and the 6 were a 5.
Okay, and what would your answer be?
15.
Okay, how many of you agree with that? Does anyone disagree? No? Marie?
I got 15 too. I took 1 away from the 6 and add on to the 9. That would make the 9 be 10. And 5 and 10 is 15.
Okay, very good.
That's all Chris said.
All right, Chi-Ha, do you have another way?
I knew 9 plus 7 was 16, so I took 1 away, made 15.
Very good. Brent?
I took 2 off of the 9 that made that, no, 3 off of the 9 that made that 6, and that would be 12, and then add the 3 on, and that would be 15.
Okay, so Brent took 3 off and started with 6 plus 6 because he knew 6 plus 6 was 12, and then added 3 back onto 12, and 12 and 3. Good. That's a good way.
Children remember doubles such as 5 plus 5 and 6 plus 6 more easily than combinations like 4 plus 3. Brent used the double he knew to figure out what he didn't know. Children also tried to make 10, and Chris changed the problem to 10 plus 5. They thus go from single-digit addition to double digits while thinking about a 10. The teacher went on to double-digit addition.
Suppose we have 13 plus 13. What's the best way to get this answer? All right, Jared.
I put the 2 10s and put them together, and I made 20, and then the 2 3s together, and those made 6, and I added 26, and it made 26.
Oh, that was the same way I did it.
So how you did it?
The same way I did it. Like one, if there's like a 10, and you have the 1 the rest of the way all the way to 20, 19, those count as 10s. So I counted those 2 as 10s, and then those 3 as 6s. So I knew I had 20, and then took those and added those together, and that's 26.
Okay. Did anyone today, it looks like a lot of you changed your mind. Did anyone think of this as being 1 plus 1 today?
No.
Joe, did you? Okay, is this a 1 and a 1?
No. It's a 10.
I couldn't trick you today. All right, I have one that we've never tried before.
Oh. 5 and 5.
Put on your thinking caps. And let's see what happens when we do one like this. Let's see who can be the first. 17 plus 13. I already have hands up.
Easy. Easy.
Brent?
30.
30?
Agree.
Does anyone disagree? No?
Finally, Kenny done good.
Okay, who would like to explain it? All right, Carrie Mann.
I took the 10, and I knew that was funny, and I knew that 7 and 3 was 10. That's all the other way I did it. That's how I did it. That's all the other way I did it. That's all real.
All right, Brent, how did you do it? Shh, listen to me.
I counted those ones as 10s, and then I knew that 7 and 3 was another 10, so 20, and then count that is another 10, that's 30.
All right, very good. I have one more for you to try that we haven't done yet. You did very well on that one. 26 and 5. Already?
See that? That on the board, I had my hand up, but my hand up right when I saw these.
My goodness, you're fast today.
It was easy.
Chee-haw.
30. Disagree.
Joe?
31.
All right. Joe, would you like to tell us what you got? I have more agreements for you.
I took the one off the I took the one off the 6, not the 6, and then
Okay.
that was 5, and then I mean 5 and 5 was 30, and then 5 and 5 was 10, and then that was 30, and then 31.
All right, very good.
That's how I did it.
Okay, Gary, can you sit flat? Okay.
But that's fucking so
This one?
yeah. I put the 26 and then after I at 26 I put the 20 and then 20 and then added the 6 and the 5 together, and I knew that was 11. So I put the 11 onto the 20 and then I knew it was 31.
31. All right, Chris?
This is how I did it. I took the 1 off the 26.
Okay, I'm going to change that. So what did that make that?
25.
Okay.
And then I put 25 and 5 together and it made 30. Then with that extra 1, I put it on and then it made 31.
Okay, very good. Chris, you know that's about how I did it too. If you take what you already know, if you know 25 and 5 is 30, then just put the other one back on. That's a very quick way. Chris, do you have a different way?
I knew that 26 plus 4 was 30, and add 1 more to the 4, and then it's 31.
Good. So if you know 26 and 4 would be 30, just add 1 more to it and you've got 31.
We've just seen 4 different ways of solving this problem. Joe added 5 and 5 to make 10, while Gary added 6 and 5. The first Chris changed the problem to 25 plus 5 plus 1, but the other Chris changed it to 26 plus 4 plus 1. Children's creativity is boundless. These children are inventive in part because they've never had any worksheets or drill in first grade arithmetic. They're excited by their own inventions and are proud to show them off. Teachers who allow children to exercise their own creativity marvel at the variety of unexpected ideas children come up with. Piaget's theory makes us focus on children's own natural ability to think and to create arithmetic. What you've just seen reflects an attempt to develop this ability in double column addition. Application of the theory here suggests that much more can be learned from children in constructing the next level of our knowledge about how children reinvent arithmetic.
Jared?
64.
Jared, can you explain how you got 64?
Just knew it.
Just knew it?
I knew it.
Okay, Elizabeth?
I knew that